Hi, we are from the group Logic Q and this is our group presentation for mathematical logic and proving technique.
What is this subject about? This subject is a foundation course for students majoring in mathematics at undergraduate level. Students will learn set theory, truth and falsity of statements, construction of truth tables, laws of logic and various methods of proving. Even though the subject is tailored toward the usage of logic in mathematics by using symbolic logic, students will find it useful in everyday life usage. The topics that we are going to share is logical implication, arguments and rules of inference, the forward-backward method, definition and mathematical terminology, and the construction method. Enjoy the video!
Hello, today I will share about logical implication. Logical implication is a type of relationship between two statements or sentences. The relation translates verbally into logically implies, or if then and it is symbolized by a double line arrow pointing toward the right. If A and B represent statements, then A arrow B means A implies B, or if A then B. The word implies is used in the strongest possible sense. Actually, there are many ways how to read the logical implication. Let's say we have two simple statements P and Q, which is joined by the implication operator P implies Q. P is known as the hypothesis and Q is known as the conclusion. P arrow Q can be read as P implies Q, P implies Q if P then Q, P only if Q. If P is sufficient for Q, Q is necessary for P, Q follows from P, or Q if P. The true value of the compound statements P implies Q is true when both the simple statements P and Q are true. P implies Q is always true if P is false. The only scenario that P implies Q is false happens when P is true and Q is false. For examples, let's say we have P. P is you try hard for your exam and Q is you succeed. So, if you try hard for your exam, then you will succeed, or if you succeed, then you try hard for your exam. Another example is in a logical tautology, the statement is always true because one half of the or contraction must be so. Examples: either it will rain tomorrow or it won't rain. She is brave or she is not brave. I will not get in trouble or I will get in trouble.
Hi, I'm Arisa and I will be continuing our presentation with the topic arguments and rules of inference. What is argument? Argument is a list of statements called premises followed by the final statement called conclusion. Our premises is also known as our hypothesis, and our argument is valid if each of the premises are true and the conclusion is also true. There are three ways to determine the validity of an argument. The first one is truth table, the second one is laws of logic, and the third one is rules of inference. What is rules of inference? Well, it is a way to determine the validity of an argument which involve more than 3 propositions. There are 8 rules in total, and it is modus ponens, modus tollens, law of syllogism, rule of conjunction, rule of disjunctive syllogism, rule of conjunctive simplification, rule of disjunctive implication, and rule of contradiction. For modus ponens, we have P, P implies Q, and conclusion Q. For example, Inosuke wins a fight, P. If Inosuke wins a fight, then Inosuke is happy, P implies Q. Therefore, Inosuke is happy, conclusion Q. Law of syllogism, P implies Q, Q implies R, conclusion P implies R. Example, if Razor is a bartender, then he is unhappy, P implies Q. If Razor is unhappy, then he cries, Q implies R. Therefore, bartender cries. Conclusion, P implies R. Rule of conjunction, we have P, Q, and conclusion P and Q. Example, Hu Tao went to the funeral, P, Zhongli went to the funeral, Q, therefore Hu Tao and Zhongli went to the funeral. conclusion P and Q. Modest tolerance, P implies Q, negation Q, and conclusion negation P. For example, if it is cold, then Diluk wears a coat, P implies Q. Diluk is not wearing a coat, negation Q, therefore it is not cold. Conclusion negation P. Rule of disjunctive syllogism, P or Q, and then we have negation P, our conclusion will be Q. For example, Mango will eat fish or chicken, P or Q. Mango does not eat fish, negation P, therefore Mango eats chicken. Conclusion Q. Rule of conjunctive simplification, there's two, P and Q, conclusion P, or P and Q, conclusion Q. For example, Albedo and Klee went to the fair, P and Q. Number one, therefore Albedo went to the fair, conclusion P, or the second one, therefore Klee went to the fair, conclusion Q. Rule of disjunctive implication, also known as rules of addition, P, conclusion P or Q. Example, Liana comes to the prom, P, therefore Liana or Rowan comes to the prom, P or Q. Rule of contradiction, negation P implies F note, then we have conclusion P. For example, if Alian is not sick, then today is Monday and today is not Monday, therefore Alian is sick. Now let's look at some examples related to arguments and rules of inference. Example number 1. Consider the following propositions. P. It's sunny this afternoon. Q. It's colder than yesterday. R. We will go swimming. S. We will take a canoe trip. T. We will be home by sunset. Step number 1. We always need to change the premises into symbolic logic first. So, A. It's not sunny and it's colder than yesterday. Negation P and Q. B. If we go swimming, then it's sunny. R implies P. C. If we don't go swimming, then we will take canoe trip. Negation R implies S. D. If we take canoe trip, then we will be home by sunset. S implies T. As the conclusion, we will be home by sunset. T. Step number 2, we use rules of inference to find out whether the argument is valid or invalid. Number 1, negation P and Q. We get this from our premise just now. Number 2, negation P. We will get negation P by using conjunctive simplification rule in 1. 3, R implies P, also from our premise. 4, negation R. We got negation R by using modest tolerance on 2 and 3. 5, negation R implies S, also from our premise. Number 6, we got S from using modest ponens on 4 and 5. 7, S implies T, our premise. And 8, we got T from using modest ponens in 6 and 7. Step 3, we need to state whether the argument is valid or invalid. Since our answer is the same with the question, which is T, therefore the argument is valid. For example number 2, 1. If it is Saturday today, then we play soccer or basketball. 2. If the soccer field is occupied, then we don't play soccer. 3. It is Saturday today and the soccer field is occupied. Proof we play basketball or volleyball. Step 1. Extract all primitive proposition and denote them with PQR and so on. Primitive proposition is a statement where logical operator does not exist. So P, it is Saturday today. Q, we play soccer. R, we play basketball. S, the soccer field is occupied. And T, we play volleyball. Step 2. Change the premises into symbolic logic. Number 1. If it is Saturday today, then we play soccer ball or basketball. P implies Q or R. 2. If the soccer field is occupied, then we don't play soccer. S implies negation Q. Number 3. It is Saturday today and the soccer field is occupied. P, S. Proof we play basketball or volleyball. R or T. Step 3. Use rules of inference to find out whether the argument is valid or invalid. Number 1. P implies Q or R. We got this from our premise. Number 2. P is also from our premise. Number 3. And number 3. Q or R. We got this from using modest ponens in 1 and 2. Number 4. S implies negation Q, our premise. And number 5. S is also our premise from the question number 3. We got negation Q by using modest ponens in 4 and 5. Number 7, R. We got R by using disjunctive syllogism in 3 and 6. Number 8, we got R or T by applying addition rule to 7. Step 4, state whether the argument is valid or invalid. Since our answer is the same with the question, which is R or T, then the argument is valid. Example 3, prove the validity of negation A or B implies C, negation A, negation C, conclusion B. So the solution is number 1, negation A or B implies C, our premise, and number 2, negation C, also our premise. Number 3, we got A or B by applying modest tolerance in 1 and 2. Number 4, negation A is our premise. Number 5, we got B by using disjunctive syllogism rule in 3 and 4. So since we got conclusion B, the same as the question, then our argument is valid. That's all from me. Thank you. Hi, I'm Nur Shamila. So I'm going to presenting the first subtopic of the chapter 3, which is the forward-backward method. Let's see, this is all the content that I will show you guys in my presentation. There are some introduction to proof, the hypothesis and the conclusion, the forward and backward process, and some examples. Let's take a look to the introduction to proof. In mathematics, a statement is considered as a sentence or proposition that will be either true or false, while proof is a convincing argument that can be expressed in the language of mathematics. The very first step in doing proof is to identify the hypothesis A and the conclusion B. It is easy to conclude a statement whether true or false by the implication if A, then B. In this chapter, we are going to discuss about the various proof techniques that we all use in proof regardless of subject matter. Okay, for the hypothesis and the conclusion, if the implication are not written in the specific form, thus everything that assumed to be true is going to be statement A, which is hypothesis. While the conclusion of the statement or statement that need to be proved is going to be the statement B, which is conclusion. For example, if A and B are even integers, then A plus B squared is divisible by 4. For this statement, we got the hypothesis is A and B are even integers, while the conclusion is A plus B squared is divisible by 4. After we recognize what is the hypothesis and the conclusion for the statement, so we can assume that statement A is true, and use any formula or information related to reach the conclusion that B is true. Okay, backward process is writing the proof to reach the conclusion that B is true. While forward process is when we deriving from statement A, which is assumed to be true, to another statement which is A1. And the last statement will link up to the statement that obtained in the backward process. Okay, the very first example about the question that involving the forward-backward method is, given that if n is an odd integer, then n squared is an odd integer. Prove it by using the forward-backward method. Your answer should have an analysis of the proof and the condensed proof. We got the statement A is n is an odd integer and statement B is n squared is an odd integer. If we refer to the definition of odd, an integer n is odd if and only if n equal to 2k plus 1 for some integer k. So we can write the statement B1 to n squared equal to 2k plus 1 for some integer k, and A1 is n equal to 2p plus 1 for some integer p. We just do the forward process of the statement A2, which is we square root the left hand side and the right hand side of n equal to 2p plus 1. So we got 2p plus 1 and times 2p plus 1. And then lastly we factorize it back into 2p squared plus 2p plus 1. So if you look the statement 2k plus 1, if k equal to 2p2 plus 2p is equal to b1. So this statement is equivalent to the statement b1. In the condensed proof, we just explain what happened in the analysis proof. Okay, for example, from the hypothesis, n is an odd integer. By the definition of odd integer, n equal to 2p plus 1, squaring the left hand side and right hand side of n equal to 2p plus 1, we will get n squared equal to 4p squared plus 4p plus 1. Factoring 2 from the right hand side, we will get 2 times 2p squared plus 2p plus 1, and this will equal to 2k plus 1, where k equal to 2p2 plus 2p equal. Thus, n squared is equal to 2k plus 1 for some integer k, and n squared is an odd integer. Okay, for another example of question that involving the forward-backward method is, given that if the triangle RST is equilateral and SU is a perpendicular bisector of RT, then the area of triangle RST equal to square root of 3 times RS squared over 4. Prove it by using the forward-backward method. Your answer should have an analysis of the proof and the condensed proof. Okay, for the solution, we just do the same things to the previous one. We just identify which is the statement A and the statement B, and then we draw a triangle that show how it look like. We just write the B1, okay, RST equal to the area of the triangle RST, which is square root of 3 times by RS squared over 4. From the statement A, we got the triangle RST is equilateral, so all the side is equal. So we can write the statement A1 is RT equal to RS equal to ST. And then we just write the general formula of the area of triangle, which is 1 over 2 times by height and base. So we write as 1 over 2 times by RT and SU. And then we just change the position of the SU so that we can get the area of SU using the formula of theorem Pythagoras. From the theorem, we can get the RU is equal to 1 over 2 times by RT. So we change the RU in the theorem to 1 over 2 times RT. And then we simplify the equation, we'll get the last statement, which is square root 3 RS over 2. And then we put it into the formula of area of triangle, and then we get square root of 3 times RS squared over 4. So it is proved that it is equivalent to the statement B1. To do the condensed proof, we just explain what happening in the analysis proof. So we got from the hypothesis, since RST is an equilateral triangle, RT equal to RS equal to ST. By using formula of area of triangle, area RST equal to 1 over 2 RT times SU. So line SU is a perpendicular bisector of RT, and by using theorem Pythagoras, SU equal to square root of RS square minus RU square. RU is half of RT. So by substitute RU equal to 1 over 2 RT and RT equal to RS in SU, we get SU equal to square root of 3RS over 2. So substitute SU in the area of a triangle formula. So we get 1 over 2 times RS equal to square root of 3RS over 2. So it also equal to square root of 3RS square over 4. So that's all from me about the forward and backward method. Let's go to the next presenter. Thank you.
Hi, I'm intern Shaira binti Mazlan, ID number 2020-815714. Chapter 3, Proof 3.2 and 3.3. Definition and mathematical terminology. Definition and mathematical terminology. A mathematical definition is an agreement by all parties concerned as to the meaning of a particular term or concept. Definition 1. N divided M denotes as N divided M if M equals to Kn. Definition 2. A positive integer p bigger than 1 is prime if the only positive integer that divides p are 1 and p. Definition 3. A triangle is isosceles if its two sides have equal length. Definition 4. Two pairs of real number x1, y2 and x2, y2 are equal if x1 equals to x2 and y1 equals to y2. Definition 5. An integer n is an even if only if the remainder on dividing n by 2 is 0, or n is even if and only if n equals to 2k. Definition 6. An integer n is odd if only if n equals to 2k plus 1 for some integer k. Definition 7. A real number r is irrational if and only if r can be expressed as the ratio of two integers p and q, where q is not equals to 0. Definition 8. Two statements a and b are equivalent if and only if implies b and b implies a. Definition 9. A intercept b is true if and only if a is true and b is true. Definition 10. A union b is true in all cases except when a is false and b is false. 3.3. Mathematical terminology. 1. Proposition, a true statement that you try to prove. 2. Theorem, a proposition which is extremely important. 3. Lemma, preliminary proposition that used in the proof of theorem. 4. Corollary, proposition that follow as a result of knowing that a theorem is true. 5. Axiom, certain statements that are accepted without a formal proof. 6. A implies B. When A then B, B follows from A. B is necessary for A. A is sufficient for B. A only if B. Example. First, for the proposition, a triangle is isosceles if its two sides have equal length. When the triangle have the equal length, therefore the triangle is isosceles. Theorem, we have to find hypotenuse when the triangle is 90 degrees. Therefore, we use the theorem a squared plus b squared equals to c squared. Axiom, 2 plus 2 is 4, 3 times 3 is 9. From this diagram, lines 1 and line 2, a plus b equals to 180 degrees. If a plus b equals to 180 degrees, then line 1 and line 2 are parallel. Thank you.
Now, I will explain about the construction method, which is one of subtopic in chapter 3, which is 3.4. The construction method is used when the conclusion involves an existential quantifier. The notation is there is, there are, there exist, and such that, or another word for which. Now let's look for the examples. And example number 1, if p and q are even integers, then 3p squared plus pq is divisible by 2. You also should have an analysis of proof and condensed proof. Analysis of proof is like the working solution, and the condensed proof is like you explain it in words what you will do. in working solution. So let's look at the condensed proof first. Since P and Q are even, then we can use the definition of even numbers. P equals to 2A and Q equals to 2B. AB is substituted with Z. By using the algebraic manipulation, substitutes P and Q into the equation, which will imply 3P squared plus PQ equals to 3 times root 2A squared plus root 2A times root 2B. Hence, A and B equation, we get this from the question. P for A, P and Q are even integers. B, 3P squared plus PQ is divisible by 2. From B, 3P squared plus PQ equals to 2K. It is because we interpret the information given. From A, P equals to 2A, Q equals to 2B, because we use the division of even numbers. Hence, we just need to substitute the equation. So it will become something like this, and the final answer would be 6A squared plus root 2AB. And let's another word to represent the numbers inside the bracket. So let's C equals to 6A squared plus root 2AB. Hence, the answer would be 3P squared plus PQ equals to 2C. The theory is, this question has been proved, and the final answer is this. Let's look at example number 2. Prove that if A, B, and C are integers for which A such that B and B such that C, then A such that C. For the condensed proof, since A, B, and C are integers for which A such that B and B such that C, then we can use the definition of divisible by divisible or even numbers, and we get C equals to PA, B is substituted by Z, and B equals to KA, C equals to QA, KQ is substituted Z. Then from B equals to KA, C minus B. C equals to QA, we can substitute B into C, we will get QKA minus with QKA, like P equals to QK, P substitute Z, then C equals to PA, and P substitute Z is proven. So, from the question, A is if A, B, and C are integers for which A such that B and B such that C. It is given inside the question, and B, A such that C. This one. So, from B, C equals to BA, and from A, B equals to Q, B equals to KA, and C equals to QB, because we use the definition of divisible or even numbers. From this, C will get C equals to QKA minus QKA, let P equals to QK, and the final answer would be C equals to PA, and P is substitute Z. This question has been proven, and this is the answer. That's it for this question. Let's move to example number 3. Show that x cubed minus 3x squared minus 9x minus 5 is equals to 0 is unique. Only show analysis of proof. We need to solve this question by factorizing the equation. So it will become like this: x minus with 5 times with x plus 1 in bracket. Hence, we will get the values for x is x equals to 5 and x equals to negative 1. So substitute. When x equals to 5, the answer would be 0. And when x equals to negative 1, the answer would be 0. Hence, the theory is proven, and therefore x is unique. I think that's all from me. Thank you, and have a nice day.
During this assessment, we had found that we know the concept of properties of set and operation, laws of set theory, logical connective, premises, and arguments in solving mathematical problems. We can demonstrate interpersonal skills in completing group tasks involving mathematical logic and proving techniques. We know on how to determine the appropriate laws and basic proof techniques in proving the arguments and mathematical statement. The tasks make us sharpen our ability to identify and articulate safe skills, knowledge and understanding confidently and in a variety of contexts. Demonstrate professional skill, knowledge and competencies. We will have ability to apply creative, imaginative and innovative in thinking and ideas to solve some mathematical problems.